right, good morning. Welcome to my stream. Let's switch over to my display. There we go. And we're up and running. Good. So last time, we finished function calls. And so we're able to actually call some functions, right? And I ran this command. Here it is, with the little looper program, and it ran. It's pretty nice. So the next section is, let's get rid of that. The next section is return statements. But before I do that, I wanted to take a quick peek at something I saw online. I was writing OS in Rust. That's what I want to do next. Twitter. On my Twitter. Let me take a look at that link before I scroll. Where's my tweets? Yeah, this. So the into thing is so obviously I know about into because I've been writing into, but there's this neat thing here that it didn't occur to me is possible to do. That the Rust compiler can actually into it for you. Right. So right now what I have, if I can grep toString in source rs, there's a few functions which I say t takes a toString, and then I just say name t, which is fine. It just means something toStringable. But what this is saying here is that you can actually say, instead of it being a toString, you can have an into string, and then you call name into on whatever that is. Well, how does that help? You have to do the same thing, right? I mean, that's the obvious question to ask. If we take a look at chunk, I mean, I'm calling name toString on this versus name into over here. What's the difference? Well, the difference is that name into becomes a no-op if it's already a string. That's what they're showing here, is if you have a string and you pass it in, there's 0 copies on that, you're not making an additional copy of the string. Whereas here with an ampersand str, you are converting it to a string. And that way you don't have to worry about whether or not it's a string. You don't have to do this toString business. You just say into. So I'm going to try doing that here. If I change this to into like that and then string, then I can just say into here. And everything should still work. And it doesn't. The trait from is not implemented for string. Oh, so this doesn't work? You can't. Okay, so that's different to what I just learned, isn't it? Oh, because this is a toString. This needs to be an into string. Yeah. See? Okay. So we should be able to replace all the toStrings with that. Let's go into the compiler. Oh, we already are. And so this should be into string. This becomes into. Yep. And then function. And VM is the last one. Into string. Into. So maybe this, I wonder if this can just go away. Will automatically into. Pum. Mismatched types. That's a shame. Okay, so expected string found type parameter t. I was hoping that this would just work the same way. Let's into that. Name. No, it still has an issue. Current function borrow should be a string, right? Well, we can't make a string from an ampersand string. And that's what this is. And if I do that, it's going to complain about lifetimes. Cannot move out of reference. Oh, that's a shame. Okay, so I can do that. Okay, that's not as nice. Where's toString here? I'll try it here. The reason I'm excited about this. Oh, I can do this, right? I can do ampersand t there, and then error message can just get an into here. I wonder if that'll. Oh, right. Cannot infer. Okay, so this becomes this. And that. Oh, okay, so that gets rid of all these ampersands on these guys. And that's going to be everywhere, isn't it? Yeah, okay. Very good. Okay, so that's that. So that was a pretty minor change, but it's the reason I'm excited about it. Let me show you. If is because it's not just applicable to strings, it's applicable to anything that you're doing intos on. Git add source, git commit dash. Let's see Clippy. Yeah, git commit toString converts to into string. There. Okay. Because all of our emit bytes, we have these intos on, and we don't need them anymore if we can make the first thing of the emit byte be an intuable. And this opcode is already into U8. This is all in compiler. So if I look for emit byte, what I want then is a type that can be converted into a U8. And to make this a T, and then I say byte into here, and that way it's only in one spot. And this way I can pass in either a byte or a. Okay, so this also needs the same thing. Right? Emit bytes T into U8. And then I'll have to go through each one of these calls and change that. But I think that'll clean up the code a bit. And also, I've learned something new about Rust. So all these intos can go away. That's going to be a little annoying. Into like that. So all these opcode intos can go away. And there are a lot of them. So I think this makes the code a little cleaner, right? You can just say emit byte and then pass in the opcode, or you can say emit byte and pass in a byte. Yeah, there's a lot of that can be cleaned up. Okay, oops. Current function. Oh, I don't want to change that one. This one I don't want to change either. One sec. I have a text message I need to respond to. All right. This byte isn't into already. Oh, this is the one we actually need. Okay, so that's good. So let's see, does this compile? It doesn't. Why not? Expected chunk opcode in found U8. Why is it expecting an opcode here? On emit bytes. Oh, because these have to. Oh, right. These have to be the same type. Okay. So T and U into U8. So now they can be two different types. Yeah, look at that. Okay, so we cleaned up all of those intos. And the reason we can do it is because in chunk we already had an from implemented for opcode, which gives us the into for the other direction. All right, so I think that's a nice That's a nice cleanup. Yeah. Yeah, I think that looks more legible. So let's git add source. Clippy shouldn't complain about anything here, right? And then git commit -m emit byte into U8. There, okay. So with that having been done, and now that lesson learned, we should be able to, in the future, whenever we run across these things, we can just use the into. That's an exciting one. All right. So let's get to return statements. This is what we came here for. If you want a function that returns something other than the implicit nil, you need a return statement. Let's get that working. All right. So in the compiler, in statement, we're putting it just before while. Also self is match. Token type. Return. Simple enough. When the compiler sees a return keyword, it goes here. So return statement. If we match a semicolon, then just emit the return, okay? Else, self-expression, right? Because we have to evaluate what we're returning. Self-consume, semicolon. And then self-emit byte, opcode, return. And I don't have to put the into anymore. Isn't that cool? Okay. The return value expression is optional, so the parser looks for semicolon token to tell if the value is provided. If there is no return value, the statement implicitly returns nil. Wow, okay, that's it. We already have a return function, which implicitly returns the nil. Nice. Otherwise, we're going to evaluate the expression. That'll be left on the stack, and then we'll return, leaving whatever expression on the stack. Right. So we implement that, the implicitly returning nil. We implement that by calling emit return, which emits an op nil instruction. Otherwise, we compile the return value expression and return it with an op return instruction. This is the same op return instruction we've already implemented. We don't need any new runtime code. This is quite a difference from JLOCs. There we had to use exceptions to unwind the stack when a return statement was executed. That's because what you could return from deep inside some nested block. Oh, that was because you could return from deep inside some nested blocks. Since JLOCs recursively walks the AST, that meant there were a bunch of Java method calls we needed to escape out of. Our bytecode compiler flattens that all out. We do recursive descent during parsing, but at runtime the VM's bytecode dispatch loop is completely flat. There's no recursion going on at the C level at all. So returning even from within some nested blocks is as straightforward as returning from the end of a function's body. We're not totally done though. The new return statement gives us a new compile error to worry about. Returns are useful for returning from functions, but at the top level of a LOX program is imperative code too. You shouldn't be able to return from there. Allowing return to the top level isn't the worst idea in the world. It would give you a natural way to terminate a script early. You could maybe even use a return number to indicate a process's exit code. So we've specified it's a compile error to have a return statement outside of any function, which we implement like so. So a return statement, before we even match the semicolon, we check to see if we don't have this type, do we? That was something I completely ignored. Because it wasn't helping me figure things out. So let's add one. I guess this is saying type, but it's the compile result type, right? Because we're either compiling directly into the script or we're compiling into a function, and I'm sure that's going to update later. So let's do an enum of, let's call it the chunk type. And we have script and function. And we'll add it here. C type, chunk type. And now, of course, every place we use compile result, that's going to blow up. We need a default for it, I guess. Ooh. Yeah, we can do that. Impl default for chunk type. Fn default. Self. Chunk type. We'll make it script. That way, when we initialize the script initially, it'll be a script, and then when we create the function, we can just pass in function. We have 3 warnings, probably because we're not using it anywhere. And then this is the compile result. Let's look at our compiler itself, where we generate here. This is where we generate compiler. This is going to just pull default. Right. But when we create a new one, this is the top level. Here, this is where we're creating a new one. We want to say, okay, so look at the difference here. We have compile result default for this and compile result new for that. So default is going to be script, and if we do a new, we can pass in the chunk type. Just like that, and then over here this just becomes chunk type function. That all checks. We're down to 2 warnings, probably because we're setting it but not reading it, and then here's where we're gonna actually read it. So we're gonna say if, and we have to extract this result, right? If self.result.borrow.cType is equal to chunk type. I'm gonna have to give it partial equal, aren't I? Script. Then we're gonna say self error can't return from top level code, and we just keep going because then we reset, and of course that fails because we don't have partial equal, right? Yeah, which is easy enough to add. Oops, not into derive partial EQ. Okay, so if I say cargo run, and if I just do a bare return here, it should give me that error. Error at return, can't return from top level code. But I should be able to create a function, boo, which returns a number. And let's see, it did not work. Right? We should see, it's also throwing in a nil return. That's interesting. Why? What's that all about? If I say foo now, it should put the 42 on the stack, and it does. If I say print foo, it should actually print out the 42, and it does. Okay, so this is interesting. This must be the top level script, and this is the function itself, I guess. Yeah, because we have to define this global. No, this is the top level script here where we define global and then we do a nil return. It looks like we're doing a nil return regardless of, so it's just adding an extra 2 bytes to our chunk. Right? So let's take a look at that. Oops. Source compiler. Where do we call emit return? It's called here at end compiler. Right, so regardless of whether or not we had a return statement, we're still going to emit a return. That means we have those extra 2 bytes are thrown at the end, even if we've just emitted a return statement. All right. Well, I mean, this was straightforward, and it doesn't hurt anyone, and it probably makes it more complicated than it needs to be if we try to look for it. Right, because we don't know, this return could, I can't just set a flag saying we have a return statement, because this could be anywhere in the middle of the function, right? And then if there's more statements after that, right? If, for example, if I say cargo run, if I say fun foo x, and say if x equals 12, print it's 12, return 14, and then have some more statements here that do other things. Print it's not 12, and then return nothing, right? And now if we look at this, we have the get local, compare it to 12. If it's false, we pop blah blah blah. And so here, where we're doing a return here, but if we say, okay, we have a return statement, we still need a return statement after this thing. So this is still important to have. So we'd have to keep track of, is the last thing we did a return statement? And if so, we don't need these guys. And I can imagine there might be some corner cases there as well, which would be annoying. So I'm just going to leave it. This is the bottom line on that. Okay. Get add source. And this is section 24.6. This was very fast. Return statements. That was a very fast section. All right. Native functions. Our VM is getting more powerful. We've got functions, calls, parameters, returns. You can define lots of different functions that can call each other in interesting ways, but ultimately they can't really do anything. The only user visible thing a LOX program can do, regardless of its complexity, is print. To add more capabilities, we need to expose them to the user. A programming language implementation reaches out and touches the material world through native functions. If you want to be able to write programs that check the time, read user input, or access the file system, we need to add native functions, callable from LOX, but implemented in C, that expose those capabilities. At the language level, LOX is fairly complete. It's got closures, classes, inheritance, and other fun stuff. One reason it feels like a toy language is because it has almost no native capabilities. We could turn it into a real language by adding a long list of them. However, grinding through a pile of OS operations isn't actually very educational. Once you've seen how to bind one piece of C code to LOX, you get the idea. But you do need to see one, and even a single native function requires us to build out all the machinery for interfacing LOX with C. So we'll go through that and do all the hard work. Then when that's done, we can add one tiny native function just to prove that it works. The reason we need new machinery is because from the implementation's perspective, native functions are different from LOX functions. When they are called, they don't push a call frame because there's no bytecode code for that frame to point to. They have no bytecode chunk. Instead, they somehow reference a piece of native C code. For our purposes, read native C for native Rust. We'll handle this in CLOX by defining native functions in an entirely different object type. So in Rust, in the Rust version of this, we've just been putting things here in value. And now things get complicated because I want a din. Native RC din native func. That's what I want to do. And that's going to break everything. Because we can't get partial equal, we can't get partial ORed. I don't even know if we can get debug. We probably can get debug. But this breaks this. Right. So I'll just say pub trait func. And I have no idea what goes in it. We'll figure it out when we get there. Right, so now we can't do partial ORed, partial equal. Right, that's what it's complaining about. Partial equal doesn't work for RC din native func. And I don't think I can just do impl partial equal for a I don't think I can do this because I don't define RC here. What does it take? Self and other. Returns a bool. Book. Returns a book. EQ. I'm just putting this all in one line here. To do. Oop, I forgot the brace here. Brace there. Brace there. Okay, and then the format gets formatted. Oh, it doesn't work. Okay, I guess I need to do this after all because I messed this up here. Okay. Fun. Go away. Oh. No, I'm just calling. Oh yeah, just like this. Okay. Right, so RC is not defined in the current state. So I can't define it for RC. And I don't think that I can do this and have it get into here. Right? Oh, wait, it kind of... Well, it didn't complain. Let's see if I can do it now for this as well. Partial ORD. Oh, what does that take? It's partial compare. Partial compare. And it doesn't return bool, it returns an ordering, right? Option ordering? What does this say? Yeah, option standard compare ordering. Let's just do that. Option ordering. And we can just say use. Okay, so the only thing left is debug. Is this really? Will this really work? I didn't think I could do this. Impl debug for din native func and debug. Oh, and this takes the writer and everything, right? Just like display here. Let's just copy that. Is it format or debug? To do. Okay. Let's see if this... debug is not a trait. Sure it is. Standard format debug. Okay. This might be doing the trick here. Value native func is value native RC clone func. If this works, I will be very happy. For display, value func write f native func. Right now there's no. Maybe I'll add a name to it. And that way we can get the function name. Self, return a string. And that way I can just say native no, like native like this, and then func.name. Will that work? Nope. Private field. Private field? Oh, it's because I did this. Should be native. Still have an error. Cannot move out of arg. Oh. That's, see, okay, yeah. So after all that, we learned that, yes, this is true. Even implementing partial equal and partial ORD for dynamic native func, we can't derive partial equal for the RC version of it because it has to do a move in whatever the macro is. It does not implement the copy trait. So I think what I need to do then is just write my own. Let's just try it with partial equal and see if that works for value. And now partial ORed for value. Oop, I gotta remove it from here. Yeah, okay, so if I can write those, if I can write these, and these aren't too hard to write, right? It's just annoying to write. Match, self, other, this is the way I think I did it before. And it's if it's a value Boolean A and value Boolean B, we're doing a partial compare to B, right? And we can do that with number. Nil we get for free because it's going to always be false. Can you do string partial compare? I don't think you can. Say number, and I think everything else will just say false. None, rather. Yeah, that works. Is there any reason to try to order strings? I guess we could try. Rust string partial ORed. I don't know, how do you compare strings in terms of, I mean, I guess you could do alphabetical order. That's just that. But I don't see anything about string. Sort. I don't want to sort characters in a string. Sort strings example. Oh, you can just call compare directly on the string. I guess we could do that. Why not? But does that return ordering? Value stir S, or I guess A and B. Value stir B. Is A a compare B? Oh, does partial compare work? It does. Okay. Let's go with that then. Let's roll with that. And then partial EQ is going to be... Oh, and then we can get rid of this guy, right? Oh, or do we need it for value as well? Okay, we'll find out in a second. Match self other. And this is just comparing. Actually, we can just grab these, right? Put those here. We're going to do this differently, though. We're going to just equals B. Equals B. Ordering equals, I guess. That's a little lazy to do it. If it's two nils, value nil, they're equal. That's just a true. The functions, we can compare pointers. A and B. And we could just say RC pointer EQ, A and B. We might have to ampersand those. And then the last one, equal. Oh, we can't do that. We can do false, though. The last one, we want to see if we want to compare native functions, right? That one's a little trickier. Value, because they're in a din. Native A and value native B. And what I can do is I can compare A dot type of, I guess. I think I need to import any to get that. Any Rust, any type. Standard any. Standard any. And type, do I need type ID also, or just any? Oh, type ID, not type of. Yeah, we have 3 warnings, and that's probably because we're not using native func. Let me comment this out and see what happens. Okay, so we do, okay. So you can implement this and get it as part of this guy because RC already has debug. But for some reason, implementing partial EQ for this type did not bubble its way up through the RC for whatever reason. And I don't know the reason for that because I don't know Rust as well as I should. And I think then that completes that. The warnings are, we're not using the formatter, right? And we're not constructing that variant. Both of those are correct. And that's because I want to do this for debug. I can say, I just moved down there just to say, see the display, because I think we just say right bang F, and we say native func name self.name. Right, that's all we need to do. Now we have 2 errors. Okay, so now I think that gives us all the infrastructure we need to create a native function this way. And I made it a pub trait so I could create a separate file for native functions. What they're doing here is they're creating a new value, a function. So this is a funky syntax in C. What this is saying, type def, and you're type defing this. You're creating this as a new type. And what is this type? This type is a pointer to a function which returns value. And it takes 2 arguments, the arg count and a pointer to the arguments. And that's what this is. And so instead of that, we're doing this here. And native func, I guess, we're gonna have to deal with arg count and args somehow. There's probably going to be a call with arg count and args. It's a vector value, I guess. And it returns a value. So this is the way we can do it in Rust, is we can make this. This is native fun, and I just have it inside native func, so I don't need to call it native fun. So there's the arguments right there, and it returns a value, which is right there. But in C, what this is saying, this open paren, close paren, is telling the compiler that to prioritize the star in front of the native fun. Because if you did it without the parentheses, then you wouldn't be creating a type def. You'd be creating a function declaration. But with the parentheses, it makes this. So now you can use native function, and function here is a pointer to a function which takes these 2 arguments and returns a value. And now you're shoving that in the struct. Complicated but true. All right, so the representation is simpler than object function, merely an object header and a pointer to the C function. So it's kind of similar to this in Rust, where we have a function object here, and versus a din object. So this can be made into an object because we have self parameters. If we had a function here which returned something without that, then suddenly we're going to blow up because native func can't be made into an object. It can't be made into an object because it has a function inside it that doesn't take a self parameter. So you have to make sure that anytime you want to make a din into an object, every function in the trait needs to have a self. So that's good to know. New native. For us, we're just going to create a native func, and it doesn't have any, so we don't have to worry about this either. An object type we get for free from the enum, so we don't need to worry about that. The VM also needs to know how to deallocate a native function object. we're not doing any allocation or deallocation ourselves. We're letting Rust handle that for us. And then print object. So I did that here. This just says native fun, but we can actually grab the name. We can say that native fn. Oh, this might present problems when we run our yeah, so if we look back here, this was something we were working on, the test suite for the JLOCS code. We still have work to do. Let's let that run. You can see we still have 30 tests to clean up. A whole bunch of things get skipped, apparently, in the JLOCS version. Anyway, so it might be looking for just native fun. So maybe we just leave it like that and ignore the name. We don't need the name. Is that the only place I use name? Oh. Maybe. So we can do that. And we can always add it back if it turns out it's useful. Because all this is doing is printing native fun. It doesn't print out the object. Okay. So this is all stuff that we don't need to worry about. All this baggage lets the VM treat native functions like any other object. Okay, so that's what we're doing here. You can store them in variables, pass them around, and throw them birthday parties. Okay. Of course, the operation we actually care about is calling them, using one as the left-hand operand in a call expression. Over in call value, we add another type case. Okay, so this is call value. What is this doing here? Oh, right. So we don't need this if we're not using anything from it. Okay. So that cleans that one up. And so all we have left is this, and we're about to fix that. So compiler. Oh, no, in VM. Call value. Ooh, right. So what we're doing here is I'm doing the peak up here instead of back here in the calls, which is fine. We'll leave that alone. But what we need now is value native. And what I want to do is just say fcall arg count. But now we need to figure out how to pass the arguments in. That's why I was pausing. Because the way we defined it, right, was with a vector. If we look here, I was saying vector of value. What we want to actually do is point directly at the stack. Right? What we're doing is passing in the VM's stack top minus arg count. After the call's done, we subtract the arg count plus 1 and then push the result and return true. Oh, so I don't think we can just reference the VM here. What we need to do maybe is pass the VM in. Because the equivalent of doing it here would be passing in self stack len minus arg count. Right, passing in a reference to that thing, and this would be just a slice of value. But I think that's going to end up with oops, where did I go? Call back. There we go. I think that's going to end up giving us borrow checking fits. Expected a slice. Found enum value. Oh. Let stack top equals self stack len, and then the match arm still. Oh, because I didn't return true. I guess I can just do this, right? Because I still have to do the push. Let me do this first. Let me finish this. So it's stack top minus arg count all the way to the stack top. That's what I meant to do. Ooh, are you kidding me? That works? That works? Wow, okay. Then what we're going to do is we're going to get the result. We're going to pop that many frames. Well, not frames, but that many entries off the stack. And so we'll do self stack truncate stack top minus arg count plus 1, I guess. I'm just following this here. And then push result. No, that doesn't work. Method not found. Oh, stealth stack push. Holy moly, that actually, okay, and we're still not building any. Okay, so we got to build one. I'm surprised that this works because we're passing in a reference to this into this call, and I thought this would be borrowing it the wrong way. Okay. Well, let's just barrel on and see where things break, right? The object being called is a native function. We invoke the C function right then and there. There's no need to muck with call frames or anything. We just hand off to C, get the result, and stuff it back in the stack. This makes native functions as fast as we can get. With this, users should be able to call native functions, but there aren't any to call. Without something like a foreign function interface, users can't define their own native functions. That's our job as VM implementers. We'll start with a helper to define a new native function exposed to LOX programs. All right, so what this is doing is it's creating a new it's pushing a value, pushing a string, pushing the native function on the stack. It's calling table set. So table, right? Table was our hash map of globals, right? We're passing in, it's saying set in the globals hash map using the string of the name. Zero, right? So we're just pushing on stack of 0, and stack of 1 is the function. So this is the value. So all we're doing is basically doing a globals.insert function name. Okay, well, it's saying added after runtime error. Let's see, runtime error is all the way at the bottom here. Let's write it. Define native. And I'm going to do this trick here into string. It's going to take a name of t, and it's going to take a function, which is going to be an RC of din native func. It doesn't return anything. Why are we pushing it onto the stack? Let's read. It takes a pointer to C function, and the name it will be known as in LOX. We wrap the function in obj native. Right. That's just making it a value, and then store it in a global variable with the given name. You're probably wondering why we push. Yes, I am wondering why. Why do we push and pop the name and function on the stack? That looks weird, right? Yes. This is the kind of stuff you have to worry about when garbage collection gets involved. Which we're not going to do. Because Rust does it all for us. Both copy string and new native dynamically allocate memory. That means once we have a GC, they can potentially trigger a collection. If that happens, we need to ensure the collector knows we're not done with the name and obj function, so it doesn't free them out from under us. Storing them on the value stack accomplishes that. Don't worry if you didn't follow that, it'll make a lot more sense. So this is one of the things we're going to miss out on, is learning how to implement a GC. It feels silly, but after all that work, we're going to add only one little native. All right, we added the clock function before. Okay, so I think all this becomes is self globals insert. I spell it right. Name into value native function. function. Wait, is that how you do it? That doesn't seem right. Something seems wrong. Expected RC new, RC clone. Yeah, that's all you got to do. And now what's the warning? We're still not creating it, and we're not calling define native. Okay, so now let's create a new file. Native rs. Oops, that doesn't exist. Native rs. So this is going to take use create value star. We're going to create a new native function called clock native. Struct, I guess pub struct native clock. It doesn't take any arguments, or it doesn't do anything, right? All we're going to do is implement native func for native clock, and all we need to implement for that is the call function, call, which takes self, arg count, usize, and args, was it called? Which is a slice of value. Actually, we don't need either one of those because all we're going to do is return the current time. Returns a value. Let's just say value number or value nil for now. Just oh, this isn't going to work because main mod native. Okay, so we're still never constructing it. Okay, but we have it here now, so we should be able to construct it, right? Where are we constructing it? Define native clock, and this is in init VM. Okay, so let's go back to VM. New. Okay, so oops. We'll say let mut globals equals hash map new. And we'll say globals, we'll say self-define native clock, native clock, RC, new, native clock. And then we'll just put globals here. Nope, no good. This function doesn't have a self parameter. Oh! That is true. That is absolutely 100% true. So there's no reason okay, well, we could do it the other way, right? We can do it the other way. Bum, 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 bum. Bum, 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 hash map new. We'll just say let VM equals this. Let mut VM. And then VM define native. Yeah? Nope. Not found in the scope. We need to import native. I don't know why I did it this way here and the other way in the other files. RC doesn't exist. Sure it does. Oh, expected reference. Expected trait dyn value. Doesn't this define implement? Oh, because no, there's native right there. This is strange. Oh, I have to make right value. Oh. No, I don't. This implements native func, right? If I go to native clock, implements a native func for native clock. So why is it saying it doesn't? Oh, I have to return VM. Okay, here it is. Expected reference, dyn native function, found reference, native clock. All right. Why doesn't this understand that this is a... You can't do this. I know you can't do that. Yeah, it's that we know needs to be borrowed. Why isn't this working? If we implement native, if we implement native func for native clock, this should work. Let me see. Let me try this. Let f equals value colon native clock. Maybe I can't do that. Yeah. Oh, RC. Oh. RC new. Okay, so that's allowed. Can I do this? No. Expected trait object found. Okay, so can I do this? Oh, RC. Okay. So you can do this, but if I tried to put this in here, it won't work. Right? Yeah, it doesn't like this. But we can do this. We created a new RC of native func and pass that in. And if I don't put this here, and then it blows up. But if we coerce it this way, then it works. Well, that's a little frustrating, don't you think? I wonder if there's something in the upcoming Rust spec that'll allow that to work. But if we do this, then this all works. And let's see, can we even call this now? Can I call clock? I don't want to do the fib thing yet. Print clock. Native function. So that worked. If I say clock, like that. Oh right, we didn't write the clock code yet. Duh. So let's write the clock code. We can actually take a look at locks AST. What would that be in? Oh, in under source. Do I have native functions? Yeah, let's just copy paste. Oh yeah, system time. And what else do we grab here? Oh, right, arity. We're not worried about arity? We must be worried about arity somewhere, right? So I guess we can get this. Do this here, and we have object num as okay, value, number, error. Ooh. I guess we would just panic. Can't get system time. Good enough. Right? Doesn't like that. Oh, because I did this. That's not an option. Okay, so that worked. What do we problem? Oh, okay, yeah. Don't care what the error is. Okay, so now cargo run, print clock. There it is. So if we run it, this is milliseconds, right? So this digit here is the seconds digit. 5, 6, 7, 8. Oops, 9. Going a little too fast for 1 second. Okay, cool. So this is the seconds, and that's the milliseconds. Nice. Okay, so that's working, and it looks like our stack isn't getting too big, so which means we're popping the right amount. I guess our calculation was correct. Get status. Let's see what Clippy has to say. Clippy's happy. We can try doing this. And we can print out that, so we can say cargo run, no default features, fib. Wow, fib of 35 is slow. Oh, I should do it release. It's still slow. We can write a really inefficient recursive Fibonacci function. Even better, we can measure just how inefficient it is. This is, of course, not the smartest way to calculate a Fibonacci number, but it's a good way to stress test a language implementation support for function calls. On my machine, running this in CLOX is about 5 times faster than in JLOX. That's quite an improvement. All right, so it looks like we took almost 17 seconds in release mode. That's pretty slow. It's a little slower than comparable Ruby program run in Ruby 243P205 and about 3 times faster than one run in Python 373. And we still have a lot of simple optimizations we can do in our VM. Okay, well, how long does it take for the AST version to do the same code? It's probably more than 16 seconds. All right. So reading and writing the IP field is one of the most frequent operations inside the bytecode loop. Right now we access it through a pointer to the current call frame that requires a pointer indirection, which may force the CPU to bypass the cache and hit main memory. That can be a real performance sink. All right, so in our version, it's a little worse than that because we're going through a borrow, aren't we? Let's take a look at the code here. While this thing is running over here, if we look at our VM, every time we access the IP, it's going through a ref cell. So we have to call borrow each time. Now I think the borrow goes away, if I'm not mistaken. Once we compile it, we only use the ref cell for compilation for borrow checking. But I don't think there's an extra. Okay, so this took 47 seconds. So yeah, it's about 3 times faster than our JLOX version, although he got 5 times faster. Yeah, he got 5 times faster than JLOX, and we only got 3 times faster. So obviously I'm not doing the best. I haven't written the most efficient code here. Yeah, and every time we increment the call frame, we go through this increment function. Does Rust inline functions? Oh, I can say inline always and inline never. Let's try that. See if that makes a difference. Oops. So let's go over here and see if we can inline these guys. All right. Oh, I want no default features. I don't know. I think the borrow goes away. The borrow mute goes away, right? Because then we're just getting the IP directly. Well, this just doesn't seem to be that much faster, unfortunately. Oh well. Yeah, it's actually slower. 17 seconds. So the difference between this and this, it's probably just noise. So the inlining didn't help. That's unfortunate. Getting the current frame. Oh, maybe what I can do is inline that as well. We are doing this. This is painful, right? Getting the last frame each time. Maybe this is an area that we can optimize, or we can save the last frame, and then whenever we push to the frame, we can save a reference to that. Where do we push? Here's a pop. So maybe there's some work we can do there during when we're interested in doing optimization, is just getting a reference to the current frame somewhere. And it would have to be able to be mutable. Oh no, it wouldn't have to be able to be mutable. We just want to do this here once. When we push a new frame, we'll grab a new reference to that. And when we pop, we'll grab a reference to that as well. Because after we pop, we can just use that same code. So that would be an interesting optimization that we can play around with. But meanwhile, let's go to these inline always. Because it didn't help. Check in with Clippy. I think I already did, right? Yeah. Git add source. Git commit. So we just finished up. What is this called? Native functions. 24.7 native functions. Not bad. Not bad for an hour's worth of work. We got return statements, we got native functions, and I was able to also clean up the intos. This is an interesting cleanup for me anyway. Okay, so that's done. Let's work on. Oh, let's right. So we were talking about getting the IP address into a native CPU register. I don't know Rust. Variable in CPU register. No, Rust does not have an equivalent. Rust register is only a hint. That's true. Rust ownership model prints you have a single value. Yeah. Okay. So you don't need to do that. Machine code. Core Arch module provides access to architecture-specific intrinsics, which relate to SIMD instructions. Okay. Native function calls are fast in part because we don't validate that the call passes as many arguments as the function expects. We really should, or an incorrect call to a native function without enough arguments could cause the function to read uninitialized memory. Not in Rust, right? Because what's happening here in Rust, what'll happen is because we're passing a very specific amount of entries on the slice. In fact, we shouldn't need to have to do this and pass this because the slice should tell us how big it is, right? And then if this went beyond the top of the stack, which it can't do, right? If arg count is negative, that's not going to work, and that it can't be negative. So we can't do that. And then in native, of course, we have this value thing here, and we'll panic if we try to read beyond the end of that slice. So we will not be reading uninitialized memory in the Rust version. Saying add arity checking, that would make sense for just being able to return a result here, right, and then we could return back a invalid argument count exception or something like that. Native function, right now there's no way for a native function call to signal runtime error. In real implementations, this is something we'd need to support because native functions live in the statically typed world of C, but are called from dynamically typed LuxLand. Right, so this would just require us to pass back the result, just like what I had. Okay, add some more native functions to do the things you find useful. Write some programs using those. What did you add? How do they affect the feel of the language and how practical it is? All right. It would be nice to be able to read and write files. That's the big glaring one. It would be, and the second big glaring one is the fact that we can't do input. Right? We can't ask the user for input in the middle of a thing. In the middle of a program. So, those would be the two new functions that I would add. Trying to think of what else would be immediately useful besides file I/O and standard input. I guess having standard error would be nice. That's a nice to have rather than a must have. I guess we could say we could take a look at all the POSIX system calls and go through each one of those and add a function for it. Why is the first one an Oracle? That's weird. Bind. Oh yeah, so network I/O. But this is all file system stuff here. Trut. I don't think we need that in a LOX. Yeah. File I/O. It's mostly file I/O, isn't it? And networking. The generic ioctl interface would be nice to have. Just all file I/O. MQ, message queues, right? That's interesting. I don't know how. I personally haven't written any programs, and I've been doing systems programming for a while now, let's say, and I have never used message queues. Memory mapping I have used. Reads, rename, yeah, this is mostly networking and file I/O. Oh, and shared memory. I have used shared memory. Shutdown. That's connection shutdown, not machine shutdown. Yeah, so it's basically file I/O and networking with a little bit of. I think message queues are similar to shared memory, just pass objects back and forth. And then I guess threading would be the last one. That would be interesting to add. Multi-threading. Then you'd have to add all the threading primitives, like condition variables and mutexes and stuff like that. Anyway, okay, that's my answer to number 4. Are we clean? We're clean. Let's just push this up. And then take a look at the next commits. There we go. So we've done this so far. I think we can actually get started on closures. I have a little bit more time. Or should I save yeah, I'll save closures for tomorrow. Because I want to work a little bit. I keep forgetting to work on this. This is something that's important. Let me add. I have a cargo watch here for what? Just Clippy. Can I do a cargo watch build release? Is that allowed? No. Cargo watch. Help. I should be able to put that in the command though, I thought. Yeah, I want it clear. Oh, does the -X, I have to say build release clear? Yeah, okay. And then actually I'm going to pull this out into its own. Ooh, that was weird. Why did that? I wanted to have that in a separate window. Okay, so I'm going to kill this. I'm going to open a new window for this. I'll make it smaller so we don't. And then I can say documents dev locks AST. And then that's, oops. Huh. Cargo watch -X build release -C. There. Okay, so now it'll build the release every time I change the code. All right, so let's take a look again at what's our first error and clean that. Oh, I wanted to do a less. Okay, so the first error is this guy here. Expected property name. Oh, error at ... Expected property name. Okay, so that is in our error code. Oh, not there. Oh, I mean, yeah, there we go. And this, why is this small? Oh, because it was, okay. Never mind. Let's close that window and use this guy here. Okay. There we go. Now we're up and running. We have error at ... expected property name. So this is error at this. So I think this is the error that we need to deal with. And I think what's happening here is the token type is EOF, right? So if we say if token is token type EOF, let's copy these guys. This should just be error at end, like that, else, like that. Does that reformat? It does. It builds. Okay, and then we can try running it again. Oh, I'm missing the line number. I took the wrong thing out. Token line. Oh. Oh, there's no line number for this. Right. Duh. Because it's token, it's error to end. We don't need token as string. That's the problem. Okay. Good. Error to end. Expected error to end. Okay, so now we have to do the funky thing about comparing and contrasting the output. So there's a way to do this. How do I run? Oh, I forgot to grab the error that's failing. Let's grab the error that's failing, or the test that's failing. Sorry, it's this guy here. Decimal point at end. So up here. Come on. Did I lose it? I think I lost. Oh no, here it is. I want this thing, this line here. CD build Java. Okay. Build Java. There. And then I just want to grab this and put this in here, and we're going to see what the actual error is. And I should write a little script to do this because that's annoying to have to remember. It does say error. It says line 2 error at end. Okay. So we still need line and a space. token line. Okay, and then if I run this manually, with that test, I think it matches. Looks like it matches now. Okay, good. What do we got? Ooh, okay. So now we have problems with equality. Everything, all this equality stuff should work, and it doesn't. And if I go here, and it's because I'm not doing a good job about extracting. So I think this is going to take some bit of, right? This is going to take a little bit of refactoring. We got true, false, false, true, illegal expression, line 7, and then an empty line. Okay, so obviously there's some issues going on here. There's this error here. That's what's coming out. But we are getting illegal expression, so let's take a look at the 5th line on that. So these all work. It's when we compare this, we're expecting a false. So that means let's look for where we have an illegal expression. In our interpreter. Okay, so this is what's failing here. Is I'm saying, okay, we're going to compare new numbers with these operands. If we have addition, we're going to create a new string. We're going to right, if we're adding a string to a number or a number to a string, those all do the thing. Here's a bool and bool, nil and nil, nil and nothing. Oh, nil and anything should work. Do we have any nils? We don't have any nils in here. Okay, so what's failing is we have a Boolean and a number, and I don't have that case here. I do have this thing here where it says arithmetic error. So not equal to other types. So what we can do is we can insert this new object, bool, something, with anything, and return false. Right? If we do that, that should clean up all of these guys, and we want to do it the other way as well. Oh, I guess we could just, instead of saying arithmetic error, we could just say bool false this way, right? Every other type is not equal to every other type. Is that the simplest solution? It doesn't work because these last 5 are true, and here these last n are false. So, because we're expecting true. Okay. True is not equal to 1. That is true. Oh, okay. So we can just match op. And token type bang equal. If it's not equal, it's true that it's not equal. And if it's equal, it's false that it's equals. And everything else is an object arithmetic error. Does that work? Compiles. Okay. All right. So let's see if that passes. Ooh, nice. Okay, we're good. We're getting much better. How many we got? We only fixed 3 tests after all of that. Man. I was hoping it would fix a bunch of issues. Statement initializer. Error at close paren expected semicolon after expression. And this one also. All right, let's take a look at what that code looks like. Oh, it's not supposed to accept a block inside there. If I run my code, it just says error at open brace, expect expression. Oh, I see. Then it carries on. Error at close paren, expect semicolon after expression. Why is it doing this, though, on line 3? Well, maybe it's ignoring this whole thing altogether, and then thinking that this is the initializer, this is the comparison, and it's expecting the incrementer here. Parser. Where do we have this? Expect expression. Oh, this would be in a for statement, right? For. Yeah, for statement. Expect this after for. So there's the initializer, right? If it's a match of a semicolon, then we carry on. If it's a match of a var, oh, we're aborting right here. Right, so if we don't get the expression statement, we say, uh-oh, we were expecting an expression. What JLOX is doing is it's carrying on, and what I'm doing here is I'm aborting right away. I think that might be a cleaner way to go. Because we're not actually, if expression statement fails, right? It's because this expression fails. Which assignments? Yeah, we have to bubble our way all the way down, right? Because this calls assignment, and this calls assignments or things like this. Here's the error. Oh no. This is where we report the error. Yeah, so it says LOX had error is true. So if this is where we're going, then we are setting the error flag, which is nice. So we could, in our for statement, just carry on and just let initializer. We can say self expression statement dot okay. Oh, why is this screen suddenly flashing when I hit the bell? Oh, like that. And that'll give us back a sum or a none. And then we will have had the error. Let me see if... Oh, no, we have to consume it. We have to consume the open brace. Right, because then we want to move on to the... Or we have to synchronize. Let I equals this if I equals none is none. And we have to self-synchronize, I think. Oh, and then return I. right? And then that would allow us to synchronize there. Undefined variable A. So I guess synchronization is not the answer. Okay, so let's undo all that mess. And we'll get back to the previous, oops, I forgot to wait. There we go. All right, so I guess what we can do is we can look at how it was implemented in JLOCs, which is here, up, control flow, right? For statement. We consume this. It's okay, yeah, so this is setting the error. Yeah, I forgot, the for statement is kind of confusing because we convert it into a while loop. But consume itself, does that throw an exception? That's something we added way at the beginning. Parsing, right? Oh, we already had consume? No. Maybe I just didn't look far enough. Here's consume. Yes. So consume throws an error, right? So it throws an exception, which means that we're doing the right thing in terms of consuming the open paren. If we look at control flow and our for statement, if this fails, we're going to throw. Oh, here, we're checking match on semicolon. Then the initializer is null. If we fail to match, okay, so I guess we need to look at expression statement, which probably isn't here. Of course not. What would it be in this one? It's not in there either. Statements. Oh, because it's a statement. This consumes. Yeah, expect semicolon after expression. So after we get that, oops, it's not in that window, it's in this one. After we get that semicolon, oh. This is what we're seeing. Huh. So maybe our synchronized code is bad. If we see a semicolon, we return. If it matches any one of these guys, we return. Otherwise, we advance. Yeah, I don't know why we would get both of these errors. That's confusing. All right. What are the other errors? Maybe there's another one. Maybe there's an easy one we can take a look at. Expected runtime error. Operands must be integers and got illegal expression. Well, this I should be able to fix in interpreter. Right, this is what's coming out here. If we're getting arithmetic error, we say illegal expression. I can just say operands must be numbers. Oh, or operands must be two numbers or two strings. Okay. So the reason we would see that was for the minus/*+, and I guess for all these guys as well. If the opcode is not one of these, or sorry, if the token type is not one of these, then yeah, so this is subtract greater or equal, add nil to nil. And so we can actually change this. We can come up with different error types for each one of these. So object, right? We have nil. We have arithmetic error. So we can just say number error, I guess. Yeah, let's leave arithmetic error being the number error. Match result. Object, arithmetic error. Is this. Everything else is going to be okay result. Like that. And then we can also have an object nums or strings. Right? And that's for add nil to nil. We can change that. Nums or strings. Error. Can make this is the operands must be numbers, and this is operands must be 2 numbers or 2 strings. Oh, except I added the ability to add strings and numbers together to get a string. Okay. So let's see what this does. This doesn't like it because this is non-exhaustive. There. Problem solved. Okay. Let's see how badly I messed things up. All right, so we're getting better. There's only 13 failing now. So let's fix this one. Adding nil to nil. Nums or strings, I guess. Oh, error. I forgot the word error. Okay. So we're from 13 to 12. Okay. Well, knocking these down one at a time. Add string to nil or add bool to a nil. I guess we can do this. Object nil. All right, and that should take care of these guys. Nine tests failed. Okay, and then what's this? This is adding a bool to a string. We should be getting that. So we can do the same thing, right? Object bool to an object stir, or the other way around. Is that going to let me do that? Because the it might not let me do that. Object nums or strings error. I guess we have to do the bang equals and the equals. Those should be allowed, right? So match up those, and then this becomes this, And then if it's true that they're not equal, and it's false that they're equal. This is really ugly looking code. All right, let's see if this test passed. Add bool string, or if I broke things. 8. We're down to 8. Nice. Okay. Operand must be a number and got none. Negate no num. What does that mean? Expected error code 70 and got 0. What does that test look like? Minus S. And what happens when I run this? And of course, I've forgotten how to do that. It all works, it doesn't complain, and it returns 0. So I'm negating a string. So that's a visit unary expr. If it's a minus, and it's a number, oh, and then we return nil. Okay. All right, so we should be returning a LOX result. It shouldn't just ignore it. It should actually return an error. Right, so we say error. LOX result, error, expr operator, runtime. It's a runtime error. Expr operator. Operand must be a number. Right? Okay. Let's see if that works. Look at that. We're down to 7 failing tests. This one I'm gonna this is another equals thing, so that's gonna be painful. All right. So I think we're good. We spent enough time on this, right? Let's check in with Clippy. I don't think I did anything Clippy worthy. Diff. It's a bunch of error cleanup. Errors and operators. Get log. What do I gotta fix that flash. That flash is really annoying. Click clean up output to conform. Git add source. Git commit -m. More Dart test cleanup. Let's push that. I pushed the other one, right? Yeah. Okay. So we're good. So okay. So tomorrow we'll start with closures, and then maybe hopefully get the last of the errors cleaned up on this guy. I think if I don't pipe it, it's kind of pretty printed, isn't it? Yeah. So we can see this is much cleaner now. If it's all on one page, I don't need to use the less command anymore. I can ignore all this skip stuff. All right. Very nice. Very nice. We're getting really close with this guy. And then we're going to have to run CLOX at some point. Okay. So that's that. I don't see anybody else streaming Rust except for me. Right now, at least. So that's unfortunate, but that's the way it goes. Otherwise, we'd go raid. And yeah, that's my stream. I will see you tomorrow for closures. I hope you have a great rest of your day, and take care.